Next, we're going to talk about vectors in space. I'm going to go through this section pretty quickly. Even if I don't write everything out, it is typed out in your notes, but it's basically the same as vectors in the plane, but adding on a third dimension. Okay, so space looks like this. We have the x-plane and the y-plane, which are the same as always. Okay, if you kind of turn the screen a little bit, then you'll see x and y. And then z comes up vertically from there. The distance formula in space is, well, first of all, a point in space is x, y, z. So the distance formula is the same, except for you add on z2 minus z sub 2 minus z sub 1 squared. So example 1 wants to find the distance from p sub 1 to p sub 2. We'll just take negative, let's see, we'll start with 3 minus negative 2 squared plus negative 4 minus 5 squared plus 6 minus 1 squared. That gives us the square root of 25 plus 81 plus 25, which is the square root of 131, which cannot be simplified. And that's it. So vectors in space, instead of just having AI and BJ, we now have CK. And A, B, and C are the components. The vector whose point is at the origin is the position vector. This is kind of just a review of what we've already talked about. So position vectors in space, same as before. You can take the second point minus the first point, each term, x, y, and z, and that will give us our position vector. So example 2 says find the position vector of the vector p sub 1, p sub 2 if we have p sub 1 and p sub 2. So it would be 4 minus negative 2i plus 3 minus 5j plus 6 minus 1k, which just gives us 6i minus 2j plus 5k. Properties of vectors in space are just like vectors in the plane. Okay, you can add, you can subtract, you can multiply by a scalar, you can find the magnitude. So V sub 1, V plus W would just be 3 plus 5i plus negative 2 plus 7j plus 4 plus 2k. So we get 8i plus 5j plus 6k. V minus w, subtract each component. So 3 minus 5i plus negative 2 minus 7j plus 4 minus 2k. And that'll give us negative 2i minus 9j plus 2k. Four times the vector v. We'll just go through and do 4 times 3i plus 4 times negative 2j plus 4 times 4k. And that gives us 12i minus 8j plus 16k. 5v minus 4w. We're just going through and multiplying and then adding. So 5v would be 5 times 3 is 15i. 5 times negative 2 is minus 10j. 5 times 4 is negative 20k. I've not left myself a lot of space here. So I'm just going to, let's see. Ah, there it is. Okay, here. Bear with me a second. I'll get this out of the way. Okay, I did my best to pause and white out. Okay, so now we've got minus 4 times w. So 4 times 5 is 20i. 4 times 7 is 28j. And 4 times 2 is 8k. 15 minus 20 is 5i. Negative 10 minus 28, that'll be negative 38j. And negative 20 minus 8, well, let's see. I think that was a positive 20. Sorry about that. 20 minus 8 is 12k. And then this last part here says find the magnitude of v. So that would be the square root of 3 squared plus negative 2 squared plus 4 squared, which is the square root of 29. The unit vector is the same in space as it is in the plane. The unit vector u would be the vector divided by its magnitude. So example 5 says, find the unit vector in the same direction as v. So u would be v divided by the magnitude of v. So that would be 6 squared, square root of 6 squared plus negative 2 squared plus 9 squared. That is 6i minus 2j plus 9k divided by the square root of 121, which is 11. So that's 6 over 11i minus 2 over 11j plus 9 over 11k. Dot product, same, except you're adding on the end c sub 1 times c sub 2. So the dot product of v and w would be 6 times 2 plus negative 2 times 3 plus 9 times negative 4. That's going to give us negative 30. The dot product of W dot V would be 2 times 6 plus 3 times negative 2 plus negative 4 times 9, which will also be negative 30. Dot product of V and V, 6 times 6 plus negative 2 times negative 2 plus 9 times 9. That is 121. And W dot W would just be 2 times 2 plus 3 times 3 plus negative 4 times negative 4, or 29. The magnitude of V, square root of 6 squared plus negative 2 squared plus 9 squared, gives us a square root of 121, or 11. And the magnitude of W would be the square root of 2 squared plus 3 squared plus negative 4 squared, which is the square root of 29. So all just the same as we did dot product in the plane. And properties of the dot product are the same in space. Angle between the vectors is the same for space. Cosine of the angle is equal to V dot W over the magnitude of V times the magnitude of W. So find the angle between U and V here. Then first, let's see, so cosine of theta is V dot W over the magnitude of V times the magnitude of W. V dot W would be 6 times 5 plus negative 2 times 1 plus 9 times negative 4. The magnitude of V is, oh, wait a minute. I've got U and V here instead of V and W, don't I? Let me make sure I'm doing it in the right order. Okay, so I'm just going to change my letters here. Sorry about that. U dot V, so we don't get confused. Same deal. Okay, so the magnitude of U is square root of 6 squared plus negative 2 squared plus 9 squared, and the magnitude of V is the square root of 5 squared plus 1 squared plus negative 4 squared. And so that is negative 8 over 11 square root of 42. So theta will be the inverse cosine of negative 8 over 11 square root of 42. Put that in your calculator. You should get 96.4 degrees. So the angle between U and V is 96.4 degrees. The direction angle. Okay, so this is a little bit more here. A non-zero vector in space can be described by specifying its magnitude and its 3 direction angles. So this is a little bit more complicated than in the plane. because there are three angles. There's the angle from the horizontal, from the other horizontal, and from the vertical. It's hard to say. The angle between V and I, between V and J, and between V and K. And here is a very complicated picture of it, which you can pause and ponder over if you like. So to find the direction angles, angle alpha is the inverse cosine of A over the magnitude of V. A being the I component of your vector. Angle beta is B over the magnitude of V. And angle, that's called lambda, is C over the magnitude of V. So example 8 wants us to find the direction angles of V. So the first thing I want to do is go ahead and find the magnitude of V, because we're going to need that for all three. So the magnitude of V would be the square root of negative 6 squared plus 2 squared plus negative 3 squared. That is 7. Nice, pretty number. Good. So, alpha will be the inverse cosine of A, which is negative 6, over the magnitude, which is 7. Put it in your calculator, you get 149 degrees. Beta will be the inverse cosine of B, which is 2, over the magnitude of V, 7. 73.4 degrees. And lambda will be the inverse cosine of C, that's negative 3, over the magnitude, 7. And that is 115.4 degrees. Okay, property of the direction cosines. So, just like in the past, you had, well, no, I guess it's not really like the Pythagorean. Anyway, if you square cosine of alpha plus the square of cosine beta plus the square of cosine lambda, so those three angles, then you actually get 1 if you add them together. So example 9 asks us, the vector V makes an angle of, you've got alpha with the positive x-axis, beta with the positive y-axis. Find lambda, the angle that it makes with the positive z-axis. So if we use this formula that we just had, cosine squared of alpha, which is pi over 4, plus cosine squared of beta, which is pi over 3, plus cosine squared of lambda will equal 1. So we can plug in. The cosine of pi over 4 is root 2 over 2. So root 2 over 2 squared plus cosine of pi over 3 is 1/2. So 1/2 squared plus lambda, or no, we still got cosine squared Yolanda equals 1. Let's see, do I have more space? Yeah. Let's take this to the next page. Okay. If you square these, you've got 2 over 4 plus 1 over 4 plus your cosine squared Yolanda equals 1. So subtract 2/4 and 1/4 from 1, and you get cosine squared of Yolanda is 1/4. Now, to find Yolanda, take the square root of both sides. So cosine of Yolanda is the square root, or positive or negative, the square root of 1/4. So cosine of Yolanda could be positive 1/2, that's the square root of 1/4, or it could be negative 1/2. So plug in, Yolanda would be the inverse cosine of 1/2, which is pi over 3, or the inverse cosine of negative 1/2, which is 2 pi over 3. Now, the definition says that the angle must be acute. So in order for the angle to be acute, it has to be less than 90. So this one's not going to work. Just this one. So Yolanda would be pi over 3. And the last example says, show that any non-zero vector in space can be written in terms of its magnitude and direction, like this. So we're just kind of proving that this could happen, that we could say the magnitude of V times the cosine of alpha I plus cosine beta J plus cosine Yolanda K. How could we do that? Well, it's actually not as bad as it sounds. We know V would be AI plus BJ plus CK. And we know that A is the magnitude of V times the cosine of alpha. And we know that B is the magnitude of V times cosine beta J. And we know that C is the magnitude of V times cosine Yolanda K. Factor out the magnitude of V, and you got it. And that concludes our section on vectors in space.